So now that we've seen the derivative of the natural log function, we're going to go back to that one case we couldn't deal with for the power rule. So we knew we couldn't reverse the power rule for 1 over x dx because that was x to the negative 1. So if we reverse that process, you'd bump up the power by 1, which would be x to the 0, divide by the new power. So this is going to cause us to divide by 0 when we go through that process. However, since the derivative of the natural log function is 1 over x, we get the antiderivative of 1 over x is the natural log of x plus c. Now, the reason we look at this in absolute values is purely for this case here. So you can go through the process. You can look at the natural log of the absolute value of x as a piecewise function. You'll be able to see that regardless of the way you write this, it's going to give you a derivative of 1 over x. But the main problem is over here, x can be negative with no issues whatsoever. No problems plugging in -2. But for my natural log function, we absolutely have problems with that because I cannot take the natural log of -2. So these absolute values ensure we don't have the log of a negative number. So ultimately, the most general antiderivative of 1 over x has to include those absolute values. So be cautious when you're going through this. If you don't put the absolute values, you don't have the problem right. Now, if you are evaluating it at bounds and the bounds make it so that it's positive, no problems then. So let's get some examples, just practicing going through now that we've got this other antiderivative tool in our kit. Let's start by evaluating the integral from 1 to 2 of 4 plus u squared divided by u cubed du. So we can go ahead and break this. We can take 4 divided by u cubed, u squared divided by u cubed. And then if you go ahead and rewrite this, that's 4u to the -3. If we go through and cancel these out, all of the u squareds disappear. We're left with 1 in the bottom, so that leaves us with 1 over u du. Now, each of these we can take the antiderivative of. So we go ahead, keep that 4, bump the power up by 1. So -3 plus 1 gives us -2. Divide by the new power. And then the antiderivative of 1 over u is natural log of the absolute value of u. And then we're going to evaluate this from 1 to 2. So before I plug it in, I'm going to go ahead and rewrite these pieces because 4 divided by -2, -2. And then u to the -2, you can bring that in the bottom. And then we'll evaluate this from 1 to 2. So going through that, if we plug in 2, that would give us -2 over 2 squared plus the natural log of the absolute value of 2. And then we're going to subtract plugging in 1. So you get -2 over 1 squared plus natural log of 1. And ultimately, the natural log of 1 is going to give us 0. So that piece is going to disappear. Then if we go ahead and simplify this, -2 over 4 is -1/2 plus the natural log of 2. And then we've got this minus here. So that cancels out and we get a plus 2. So if you do want to simplify this, -1/2 plus 2 is going to be 1.5. So that gives us 3/2 plus the natural log of 2. So you can notice here, I've got absolute value of 2, but 2 is positive. So you absolutely can drop it at that point because the inside argument is positive. Let's try a second example. We'll go through the antiderivative of 1 divided by 4x plus 1. So again, looks like a natural log because I've got x to the first power in the bottom. But because there's this 4 attached to it, I want to go ahead and make a substitution. So we're going to let u be the entire thing in the denominator. So du is 4 dx. We don't have that 4. So go ahead and bring that over. That is 1/4 du equals dx. So splitting this up, this becomes 1 over u. Dx is 1/4 du. So this is equal to 1 over u times the 4th du. So now at this point, we can pop out the 1 over 4, and then we're left with 1 over u du. The antiderivative of that is the natural log of the absolute value of u plus c. Then plugging in what our u is, that's going to be the natural log of the absolute value of 4x plus 1 plus c. So again, I need these absolute values because I have no restrictions on x back at the very beginning. So I need to make sure I'm not taking the natural log of a negative number. Let's try another example, one that looks a little complicated because I've got a polynomial over a polynomial. So what we can do is we can try rewriting this by using long division. So I want to take x squared plus 7x minus 3, and I want to go through and divide it by x minus 2. So if you remember your process, you always want to make those leading terms match up. So to get x to match the x squared, I need to multiply by x. So I put an x up top. Then we go ahead and take x and multiply it to both of these pieces, which would give us x squared minus 2. But we go ahead and change their signs. So it's negative x squared plus 2x. Now that makes these two pieces cancel out. So if I add them together, 7x plus 2x is 9x. And then we just bring that negative 3 down. Now keep doing this process. I can make those leading terms match up again by multiplying by positive 9. So I'm going to put a positive 9 up top, then go ahead and multiply this to both pieces, change the signs. So that would give me 9x minus 18. When we switch those, that gives us minus 9x plus 18. So again, these cancel out, and if we add those together, we get 15. So ultimately, this fraction I have on the inside is equal to my quotient, which is x plus 9, plus my remainder divided by that dividend. So basically the thing in the bottom. So since I'm trying to evaluate this integral, instead of this complicated thing that I can't find an antiderivative of right away, I'm going to replace it by my new equivalent expression. So we get to instead integrate x plus 9 plus 15 over x minus 2. Now the first two pieces, not so bad, but here we are going to have to make a substitution. So I'm going to go ahead, remember we can split each thing separately. Antiderivative of x is 1/2 x squared. Antiderivative of 9 is 9x. And what we're left with is we have to integrate 15 over x minus 2. So again, going to make a u sub because I've got x minus 2 in the bottom. I'm going to let u be exactly what I have in the denominator. So du is dx. So now making my substitution, my first piece stays untouched. That 15 just pops out. The inside becomes 1 over u du. So we can go ahead and find the antiderivative of that now. It's 15 natural log of the absolute value of u plus c. And then finally going back and using our substitution that u is x minus 2, I end up with 1/2 x squared plus 9x plus 15 natural log of the absolute value of x minus 2 plus c. Let's try some more. Let's go ahead and integrate 1 over x, natural log of x cubed. So again, I've got a couple pieces going on. One thing that's easiest to see though, to try to make a substitution, is I've got natural log of x inside this third power. So I think probably our best substitution is going to be to let u equal the natural log of x. So then du is 1 over x dx. So if I split this up, I've got natural log of x to the third in the denominator. You can rewrite this because you have an x in the denominator as well as a new fraction times 1 over x, because you would just go ahead and you would multiply across and get that same piece. And now we can see 1 over x dx is exactly du, and then natural log of x in that bottom turns into 1 over u. So this switches pretty nicely into the integral of 1 over u cubed du. To reverse our power rule, let's rewrite that as u to the negative 3. We go ahead, bump that power up by 1, divide by the new power, add c. Rewriting that a tiny bit, u to the negative 2 becomes 1 over u squared. And then going and plugging in what our u is, we get negative 1 over 2 natural log of x squared plus c. Let's try another fun one. Let's go through the integral of tangent of x dx. So I don't know a function that immediately has the derivative tangent of x, But because tangent can be written in terms of sines and cosines, let's try that out. Tangent of x is sine of x divided by cosine of x. And then I can break that up. That's 1 over cosine of x times sine of x. And so if you notice here, I've got 1 over a function. That's exactly my natural log. But I got to see if I make a u substitution, does that sine of x dx get sucked into the du? So if I make u to be cosine of x, then du will be negative sine of x dx. So that's great. This will get sucked into du. The only problem is I don't have this minus sign. But that's no biggie because we can just bring that over to the other side. So 1 over cosine of x turns into 1 over u. Sine of x dx just introduces a minus sign. So switching over my variables, this becomes negative times, this becomes negative integral of 1 over u du. And that's exactly negative natural log of the absolute value of u plus c, which is negative natural log of the absolute value of cosine of x plus c. Now this technically is a perfectly fine way to leave the antiderivative, but I do want to go through and I want to show you another form of this. Because if you think about some of your Pythagorean identities, sines and cosines are related, tangent and secant are related by a Pythagorean identity. Same thing with cotangent and cosecant. So what I want to do is relate tangent to secant. So one thing that's special is anything that you have as a constant out front can get sucked in as an exponent of the inside. So what we can do is we can rewrite that -1 as a power of -1 on the inside. And then thinking about what that is, cosine to the -1 is 1 over cosine, and that's exactly secant. So ultimately you get two different forms. You get one here, a second one here. But that second one I think is more intuitive, just knowing that tangent and secant are related. Even in their derivatives, those are related. So either one is fine, but I would encourage you to use the one that involves secant. So up to this point, we had only done the integral of sine and cosine because I didn't know how to handle tangent, secant, cotangent, cosecant. Cotangent is pretty identical to tangent, so we're not going to go through that one. So the last one I want to go through is secant. And this one's slightly different because you could write it as 1 over cosine, but then you can't make a substitution. So instead, this one's a little bit trickier where we're going to have to rewrite the inside just by multiplying top and bottom by something. So what we do is we take the secant function. We're going to times that by secant plus tangent divided by secant plus tangent. And so what I can do instead is multiply these two pieces together and keep that secant plus tangent in the bottom. So I get 1 over secant of x plus tangent of x. And if I distribute that secant, that gives me secant squared of x plus secant of x tangent of x. So if you notice, these are both derivatives that we're used to, and they're the exact derivatives of secant and tangent. So what we've done by introducing this new quantity and rewriting the expression, we can make a u substitution. So I'm going to let u be the thing that's in my denominator. So its derivative is exactly secant times tangent plus secant squared. So this entire thing ends up becoming du. So this substitution makes it super smooth. I end up with just 1 over u du, which is the natural log of the absolute value of u plus c, which gives us natural log of the absolute value of secant of x plus tangent of x plus c. So you can also do the same type of thing for cosecant. You're just going to change it slightly by using cosecant plus cotangent. So we're going to omit going through that. But now we've got the integrals of all of our trig functions. So if I want to find the antiderivative of sine of x dx, it's negative cosine of x plus c. We just calculated the antiderivative of tangent of x dx is negative natural log of cosine of x plus c, or a little bit clearer, that's natural log of secant of x plus c. And this I like better again because we know tangent and secant are related. The antiderivative of secant of x dx is going to be natural log of secant of x plus tangent of x plus c. So the reason I did all of these first is because all of them have co-functions, cosine, cotangent, cosecant. Their integrals are really similar, just changing by minus signs, that's all. So if we find the antiderivative of cosine, it's sine of x plus c. The antiderivative of cotangent of x, kind of relating these, would instead be a sine function, and it's going to be the opposite sign out front. So it becomes positive natural log of sine of x plus c. Likewise, instead, on the inside, I could put cosecant, but I have to change the sign out front. So that would give us negative natural log of cosecant of x plus c with those absolute values. And then finally, the antiderivative of cosecant of x plus c is again very similar to this, but negative. So we get negative natural log of cosecant of x plus cotangent of x plus c. So now we've got all of our trig functions. Let's go ahead and try some integrals. Let's evaluate the integral of secant of 1/2 x dx. Again, I've got a function inside secant, so it's going to be the smartest thing for me to do to make a u substitution, and we're going to let u be this inside quantity. So we'll set u equal to 1/2 x, so du is 1/2 dx. I'm missing this 1/2, so I go ahead and bring that to the other side or multiply both sides by 2. So 2 du is dx. So switching everything over, this becomes 2 times the integral of secant of u du. Using our table, the antiderivative of secant of u is natural log of the absolute value of secant of u plus tangent of u plus c. And again, I've got to go back to that starting variable, so I've got to use my u being 1/2 x. And so I get the antiderivative of secant of 1/2 x is 2 natural log of secant of 1/2 x plus tangent of 1/2 x plus c. Let's try another one. Let's go ahead and integrate cosine of t over 1 plus sine of t. Again, I've got a function in the bottom and then this other thing up top. So let's try making a u substitution with the thing in the bottom. We'll let u be 1 plus sine of t. So du is just going to be cosine of t. So this is going to get exactly replaced by du. And so this switches over beautifully to the integral of 1 over u du. Antiderivative of that is natural log of the absolute value of u plus c, which is natural log of the absolute value of 1 plus sine of t plus c. So I got one more. Let's integrate cosecant squared of x divided by cotangent of x. Again, want to utilize the fact that I have something in my denominator. So let's make a substitution of the thing in my denominator. So if we let u be cotangent of x, then du is negative cosecant squared of x dx. Don't have that minus sign, but that's okay. I'm just going to introduce a minus sign when I change these variables. So this becomes 1 over u in the bottom. The cosecant squared of x dx gets sucked into my du. So this becomes negative integral of 1 over u du. Again, that's just our natural log, so it's negative natural log of the absolute value of u plus c. And then plugging u as cotangent, we get negative natural log of the absolute value of cotangent of x plus c. So this covers the basis for our natural logarithmic function and also in turn now all of our trig functions. What we're going to do is now kind of take a look at inverse functions in general. And we're going to see how to find derivatives of an inverse function without maybe having to calculate the inverse. And then we will go through and we will see our exponential function more generally, and then we'll talk about other bases as well.